Welcome back, everyone. So I know in the previous video I said we're going to be heading back to SageMaker soon, but before we do that, we need to understand some fundamentals between Float32 and what Bfloat16 is actually. So you might have heard of mixed precision training, and if not, don't worry about it because we're going to cover that later. But one of the components of it is using different types of numbers. For example, it's number types. Instead of Float32, for various operations, we use Bfloat16. And keep in mind, this is a technique used to improve the training, but it should not be confused with quantization. Okay, because when you quantize a number or a training, you essentially change the data type. So you change it from, for example, Float32 to an integer. But with mixed precision training, or when we use Float32 versus Bfloat16 during training, we're not changing the type from float to integer. We're just changing it to a different type of float. So Float32 is able to hold a lot of information, but it takes up a lot more memory than, for example, a Bfloat16. And Float32 is actually a 32-bit representation, while a Bfloat16 is only 16 bits. Now, if you don't know what bits mean, we're going to cover that later. But just let's start, and I'm going to share this study guide with you, but let's just read through it, okay? So a floating point number is represented in a form of scientific notation, typically composed of three parts. This is important, okay? The sign, the exponent, and the mantissa, or also called the significand. And we're going to be visualizing this later, so don't worry about it. But when you have a number, you need a sign, either positive or negative. So that's a single bit. So when we say that a Float32 has 32 bits, we mean that the first bit actually tells the computer whether it's a positive number or a negative number. And that's going to be represented with a 0 or 1. Now, you also have the exponent, which is the second part of a type of, for example, Float32. You have the sign, exponent, and the mantissa. But keep in mind that the Bfloat16 also has the same makeup. It also has a sign, exponent, and the mantissa, but we're going to cover that later. The exponent determines the number's magnitude or range, okay? So it specifies the power to which the base is raised. So think of it this way. It tells the computer, okay, the range is from negative, 2 billion to positive 2 billion. And I just set something, okay? The exact range for Float32s is different. It's not from negative 2 billion to positive 2 billion, but it's more. But I just made up something so that you understand it, okay? The exponent is what tells the computer, okay, this number can be between this value and this value, okay? And the mantissa actually determines the number's precision. It holds the significant digits of the number. So more mantissa bits mean higher precision. So I thought I'd give a kind of representation that I found useful when I was first learning about these. So imagine you have two rulers, both of them 1 meter long, and the range is the same. They go from 0 to 1 meter. Float32 is like a ruler with millimeter markings. It's very precise. You can accurately measure 51.1 centimeter or 51.2 centimeter. However, a Bfloat16 is like a ruler that only has markings for every full centimeter. So it has the same length or range, right? It has the same exponent, which determines the range, but you can't measure with the same precision. You can see something is about 51 centimeter, but you can't tell if it's 51.1 or 51.2 centimeters, okay? So this is the trade-off. Bfloat16 keeps the same measurement length range as a Float32. That's why it's so easy to, during training, to actually use Bfloat16 because it's actually quite similar to how a Float32 behaves, but it has fewer markings, which means it has a lower precision, but it is able to save space. Now let's try to visualize these, okay? So, as you can see, the key difference between the standard 32-bit Float32, And the 16-bit brain float, Bfloat16, is how they allocate their bits between the exponent and mantissa. So over here, as we said, we have a float32, and it uses 32 bits to offer a balance of high precision and a wide dynamic range. So over here, we have 32 bits. The layout is 1 for the sign. So as you can see here in the beginning, the S, that will determine whether the number is positive or negative. Then we have the 8 exponents, which are the E's that you can see over here. We have 8 of them, and they determine the range that the number can go from, negative this value to positive this value. And then you have the 23 bits here at the end. Those are the mantissa bits, which tell the precision. Okay, so the more mantissa bits you have, the higher precision that your calculations are going to have. So it's going to be more accurate, but it's going to store it in a bigger space, so it requires more space. Now, let's look at the Bfloat16. It was designed for AI and machine learning, where a wide range is more critical than high precision. So as you can see, it's only 16 bits. It has the same 1 bit for the sign, whether it's positive or negative, and it has the same exponent bits. As you can see, it has 8 exponent bits, just like the float32. However, the mantissa bits over here are only 7. As you can see, 1, 2, 3, 4, 5, 6, 7. Compared to the float32, which has 23. So this means the Bfloat16 is not as precise. But for our calculations, it turns out that when you use Bfloat16, you get a significant amount of speed during training, and you lose only very little data in the precision trade-off, okay? So here are the key takeaways. The range is identical, both for float32 and Bfloat16. Both formats use 8 exponent bits. That means they can represent the same enormous range of numbers from approximately this to this. And Bfloat16 does not sacrifice the ability to handle very large or very small values. And here is the trade-off. The difference lies in the mantissa. So float32's 23-bit bits provide a high precision, while Bfloat16's 7 bits offer lower precision, and this trade-off makes Bfloat16 half the size, leading to significant memory savings and faster computations in hardware that support it, obviously, which is ideal for machine learning, but it also means it's a little less accurate. Okay, so now that you understand Bfloats and float32, we're going to look at a quick Google Colab notebook to see actually how much faster it is. And keep this in mind when we talk about mixed precision training, because with mixed precision training, when we have large computations, we're actually going to be using Bfloat16 instead of float32. So some numbers like or some computations like normalizations will use float32, but large matrix multiplications will use Bfloat16, and that's what we call actually mixed precision training, but more on that later. Now I will see you in the next video.